This is my entry for Wolfie's Equinox Challenge. According to the rules, I have to use a single light source, and for the globe model, the actual sun works well because it's very distant. This helps the angles have higher accuracy. But to use the sun, I have to align the globe to it. So this board is my ecliptic. I tilted it upward until it essentially cast no shadow, showing that it was properly aligned. So now I put my globe on the ecliptic. Oriented like this would be northern summer, July or so. Oriented like this would be northern winter, late December. To set this globe up for equinox, it has to be tilted like this, with the tilt of the Earth's axis completely perpendicular to the direction of the sun. In this orientation, if you look at the latitude lines on the day terminator line and imagine putting little arrows facing eastward at that point, they do, all of them point directly at the sun. That's why the sun rises perfectly eastward all over the planet during the equinox. If you do the same thing on the other side of the globe, your westward pointing arrows also point straight at the sun. That's why the sun sets perfectly west all over the globe during the equinox. Also note that the terminator corresponds with that striped vertical line on both sides of the globe, 180 degrees opposite each other. That's the prime meridian. Since the terminators are 180 degrees opposite each other and parallel with the longitude lines, this demonstrates that during equinox, day and night are 180 degrees apart for all latitudes, exactly half a turn each. So day and night are equal on the equinox. On the equator, the sun goes directly east to west from sunrise to sunset. Watch the shadow of the Lego to see that the shadow is always east-west and does not swing to the north or south. Well, within the limits of the precision of my setup. At noon, the shadow is essentially no shadow at all, showing the sun elevation is 90 degrees for 0 degrees latitude. Now I've placed the shadow stick on the 40 degrees north latitude. At noon, the length of the shadow proves that the sun is 50 degrees above the horizon. This fact of the sun elevation corresponding to latitude is evidence of the globe shape of the Earth upon which the different observers are standing. These angles of these heavenly bodies are not pointless in determining truths about the ground under our feet, as navigators discovered and proved and used the useful fact that these angles could get you from point A to point B reliably. Navigation on the ground is possible using the celestial bodies. And those angles correspond to reliable and spherically calculatable travel distances on the ground. Flat earthers who think this is meaningless are thinking very poorly. So let's talk about equatorial mounts and how their operation is consistent with globe geometry. This Lego model of an equatorial mount is on the equator. The main body is aligned north. The angle of the mount has been set to 90 degrees. What that does is make its axis of rotation parallel to the Earth's. Turned at the right speed, it exactly cancels the rotation of the Earth, so the pointer can stay pointed at the sun. See that at every part of the rotation, the stick can be oriented to not cast a shadow, proving that the stick is pointed right at the sun. Now I'm putting the mount on a 30-degree north location. Again, it's aligned to the north, and the angle set appropriate to the latitude, which is 90 degrees minus the latitude, which in this case is 60 degrees. As before, that angle has the effect of aligning the rotation axis of the mount with the Earth's axis. And as before, the mount can be rotated to track the sun, again shown by the stick not casting a shadow. This successful operation of equatorial mounts in the real world is best explained by the rotational axis of the mount being aligned to and matching another rotational axis, the axis of the Earth.